Okay, so in today's video, we are going to be looking at the question 4 of the 2023 Applied Mechanics past question of the Rivers State University. All right, the question says, draw the shear force and bending moment diagram of the beam shown in figure 4. Also compute the maximum normal stress due to the normal stress sigma equals 45 kilonewtons per meter squared. So we are given this to be the beam or the figure 4 per se. All right, and this indicates the dimensions of the beam, telling us it's simply a rectangular section. Now, we are to draw the shear force and bending moment diagram. I always say that whenever a problem is given to you in applied mechanics, the first thing to do is to what? Outline the free body diagram. That's the very first thing to do. The free body diagram is simply a diagram of force showing the entire hidden force on a given system or structure. So we start with the free body diagram, FBD. Okay, so this whole bulky diagram can just be replaced with a single line indicating the free body diagram. All right. Now at point A, we have 25 kilonewtons force acting downwards. So we indicate that here. This is point A. We have a 25 kilonewtons force acting downwards. And at point B, we have a pin support. I've always said, whenever you encounter such a reaction or such a support in any joint, this support is called a pin support. And for a pin support, we have two reactions always. One reaction is vertical to the surface, and the other is horizontal at the same point where it is acting. So it means that at point B, we have two reactions. One is vertical to the point where it is acting, the other is horizontal, same as that point where it is acting. Now we simply use RBY to indicate reaction for arrow. B simply means at point B and Y indicates vertical. So this reaction arrow can also be called force F. So it can be FBY indicating that it is a force at that point. We also have this to now be RBX. Reaction at B, at point B, X indicates horizontal. All right. Moving down to point C. At point C, we have a 50 kilonewtons force acting downward. So we can indicate that here. This is point C with a 50 kilonewtons downward force. Okay. And finally, at point D, we have a roller support. So I've said whenever you see a support like this with balls under, this simply means a roller. And for a roller support, we have just one reaction, normal to the surface. Normal simply means the reaction is always at 90 degrees to the point where the roller is occurring. And I've said in my videos on shear force and bending moment analysis that whenever the roller occurs on a horizontal beam, then it simply what has a vertical reaction. So you can have something like this. Seeing this beam is a horizontal beam, automatically this is a vertical reaction because it makes an angle of 90 degrees with the beam itself or the point of occurrence. So this is point D, this is point C. We simply call this RDY. Now let's denote their distances apart. This is 2.5, this is 3, and this is 2.5. So from A to B is 2.5 meters. From B to C is 3 meters. From C to D is also 2.5 meters. We have this. So this becomes the free body diagram. Now, the first thing to do is to find the value of the unknown reactions on this beam. We have RBX, we have RBY, and we have RDY. These are all unknown reactions. We need to find the values of these forces. To find the values of these forces, we simply employ our static equilibrium equation. So from static equilibrium equation, the equation is actually 3. Okay. The equation is actually 3 static equilibrium equation which we can employ to solving this problem. The first is the summation of the entire horizontal force acting on the beam must be equal to 0. Summation of the entire horizontal force acting on the beam must be equal to 0. So that simply means summation f of x is simply equal to what? 0. Sum all the horizontal forces and equate them to 0. Now, if you look at this beam, okay, also consider forces that point to the right to be positive and forces that point to the left horizontally to be what? Negative. So if you look at the beam, I have RBX pointing to the right. which means this horizontal force is a positive force. So you pick it out, RBX. But if you look on this beam again, there is no other horizontal force. So that means RBX is equal to 0 from the law. Summation of all horizontal forces should be equated to 0. That's the first static equilibrium law. The next law is summation of all vertical forces must be equal to 0. Summation of all vertical forces must be equal to 0. So we sum the entire vertical force, call that summation f of y, equate it to 0. Now we consider vertically upward forces to be positive and downward force to be what? Negative. Upward force positive, downward force to be negative. So we start from beginning of the beam and sum all these forces together. So let's start now. At point A, we have a 25 kilonewtons force acting downward, so it is negative. You indicate minus 25. Minus because this force is acting downwards. Moving down to point B, I have RBY pointing upwards, so this force is a positive force. So you indicate plus RBY acting upwards, so it is positive. At point C, we have 50 kilonewtons force, but now this force is acting downward, so it is negative. You indicate that as minus 50. Minus because that force is acting downwards. And finally, at point D, we have RDY pointing upward, so it is positive, plus RDY. And since we are done with all the forces on the beam, we simply equate this to what? 0. That's the second equilibrium law. The sum of all vertical force on the beam must be equal to 0. Now, let's rearrange the equation, bring the unknown terms together and the known values together. So we have RBY plus RDY. I have here minus 25 minus 50, and this is equal to 0. Sorry. All right, so RBY plus RDY minus 25 minus 50 gives us minus 75, and this is equal to 0. So we can simply send minus 75 over to this side of the equation. Negative sign cross an equal to sign becomes positive. So this simply implies that RBY plus RDY is simply equal to what? 75 kilonewtons. Call this equation 1. Now, we simply call this equation 1 because we have two unknowns in that equation and we cannot find it. Two unknowns in one equation, it is very impossible to find or to solve. Now, the only way we can be able to solve this is by considering the third equilibrium law, which is what? The moment law. Summation of the entire moment acting on the beam is equal to 0. Now, I always tell my students, whenever you're taking moments about any point on the beam, consider taking moment about the point where you have numerous of unknown reactions. Because the moment of a force about a point is 0. If you're taking moment about a point where you have numerous of unknown reactions, then the moment of those unknown reactions at that point becomes 0. That will help you to find the other unknown reactions on the beam. Now, if you look at this beam, I have two unknown reactions, RBX and RBY at point B. And I have just one unknown reaction at point D. So it will be very wise for me to take moment at point B so that the moment of these two forces about this point becomes 0. That will help me to find the moment of only this unknown reaction. So we simply take moment at point B. All right, take moment at B. Now, this is the equilibrium law. Summation of moment at point B is equal to 0. You consider clockwise moment to be positive, anti-clockwise moment to be what? Negative. Okay, so let's start now. Now, the moment of this force, this 25 kilonewtons force about point B, this force is acting downwards, which means the line of action of this force will be where? Pointing downwards. Okay, so this force will turn about in this direction. Since it is acting downward, it means it's going to turn in this direction to take moment at point B. And what turning is this? Is this clockwise or anti-clockwise? If you notice, we said let clockwise moment be positive and let anti-clockwise moment be negative. This turning is an anti-clockwise turning. So which means the moment of this force about point B is anti-clockwise. That makes it what? A negative moment. Since it's anti-clockwise, therefore it becomes minus 25 because it is an anti-clockwise moment. Total distance it takes this force to get to point B. Remember, moment is force times distance. Total distance it takes this force to get to point B is 2.5. So this becomes minus 25 times 2.5. We have this. Okay. Similarly, the moment of these two forces now at point B automatically becomes 0 because moment is force times perpendicular distance it takes the force to get to any point. So it means that the force, the line of action of the force and the point you're taking moment about must have a distance that is at 90 degrees to one another. But these two forces are directly at point B. There is no distance between those forces to point B. Since there is no distance, it means the moment becomes RBY times 0 because there is no distance. Also RBX times 0 because there is no distance. So the moment of these two forces about that point becomes 0. That is the reason why we're taking moment about point B to what? Nullify the effect of these two forces. Okay, next we move down to where the 50 kilonewtons force at point C. This force is acting downwards, which means the line of action of this force will be coming downwards. Now, I want to take moment of this force about point B. That means this force will turn about in this direction to take moment at point B. Now, what turning is this? Is this clockwise or anti-clockwise? We check again. We said let clockwise moment be what? Positive. And this is purely clockwise turning. That means the moment of this force is going to be positive about point B because it makes a clockwise moment. All right. So since it's clockwise, then it becomes positive plus 50 times total distance it takes this force to get to point B is what? 3 meters. So it becomes plus 50 times 3. Finally, you have RDY pointing upwards. That means the line of action of this force will move towards this direction. And since this force is moving upwards, that means this force will turn about in this direction to take moment at point A. So it turns in this direction to take moment at point A. Now, what direction or what turning is this? Is this clockwise or anti-clockwise? It turns in this direction. And if you check, this is what? Anti-clockwise. You said let anti-clockwise movement be negative, and that turning is anti-clockwise turning. Hence, you have that value to be what? Negative r d y times total distance it takes this force to get to point B becomes 2.5 plus 3, which is 5.5. So it becomes r dy times 5.5, and the whole of this is equal to 0. So this is the third equilibrium equation. So let's simply expand our brackets now. We have minus 25 times 2.5. That gives us minus 62.5. And next we have 50 times 3. That gives us plus 150. And finally we have 5.5 times RDY. That gives us minus 5.5 RDY, and this is equal to 0. So we evaluate now minus 62.5 plus 150. That gives us 87.5. So we have 87.5 minus 5.5 RDY to be equal to 0. Now, having found this, we simply send minus 5.5 RDY over to this side of the equation. Negative sign, cross and equal to sign becomes positive. Hence, we have 87.5 is equal to 5.5 RDY. Now, in order to find RDY, we divide both sides by what? 5.5, which is the coefficient of RDY. So this simply implies that RDY is equal to 87.5 divides 5.5. And this implies the value of RDY is equal to. So let's find 87.5 divides 5.5. That gives us approximately 15.9 kilonewtons. So this is now the value of the unknown reaction at point D, 15.9 kilonewtons. Now, having found the unknown reaction at point D, you can now substitute that value into equation 1 to find RBY, because equation 1 says RBY plus RDY equals 75. So we simply put in this value in place of RDY in equation 1. So we have RBY plus, in place of RDY, we have 15.9, and this is equal to what? 75. And therefore, to find RBY, we simply send 15.9 over to this side of the equation. So we have 75 minus 15.9. So this simply implies that RBY is equal to, so let's obtain 75 minus 15.9. That gives us 59.1 kilonewtons. So with this now, we have been able to find the unknown reactions at point B and at point D. Having found these reactions, we simply go back and plug it into the original beam. All right, so we know the reactions now. RBY has a value and RDY also has a value. RBY gave us 59.1 kilonewtons. RDY gave us 15.9 kilonewtons. Okay, so having found the values, you simply plug them back into the original diagram. Then you can now start your shear force and bending moment analysis. All right, so let's wipe here and start our analysis. All right, so first step achieved. We have found the values of the unknown reaction. So the second step now is to start the shear force analysis. Okay, shear force analysis, or you can also start the bending moment analysis. Now, what is shear force? Shear force analysis simply means the stepwise summation of the entire force acting on the beam from beginning of the beam to the end of the beam, considering vertically upward force to be positive and vertically downward force to be negative. And at the end of every shear force analysis, you must obtain 0 as the answer. So if you don't have 0 at the end, it means you're wrong somewhere. All right, let's start and see. Shear force at A simply means the force that exists at point A on the beam. Now, is this force an upward force? Then take it as positive. But if the force is a downward force, consider it to be what? Negative. And at point A, we have 25 kilonewtons force acting where? Downwards. Since it's acting downwards, it becomes minus 25 kilonewtons. Consider it always as negative. Now, this force moves from point A down to point B initially. So we simply call that shear force B prime, which means initially this same force, minus 25 kilonewtons force, move from point A down to point B. So shear force B prime is called also 20 minus 25 kilonewtons. You also take it as minus 25 kilonewtons. But on getting down at point B, it now encounters an upward force RBY pointing upwards. So since it encounters an upward force, then we have shear force B prime prime, which means finally at point B, this minus 25 kilonewtons force minus 25 encounters now an upward force. And what is the value of this upward force? 59.1. Since it is upward, you simply what? Add. It becomes plus 59.1. Now, minus 25 plus 59.1. This simply gives us 34.1 kilonewtons. So this is equal to 34.1 kilonewtons. So the shear force at B finally is 34.1 kilonewtons. Now, this same force moves from point B down to point C initially. So you indicate that as shear force C prime, which means initially at point C, this same force, 34.1 kilonewtons exists there. But on getting to point C, this force now encounters a downward force of 50 kilonewtons. So this becomes shear force C prime prime, which means finally at point C, the 34.1 kilonewtons force now encounters a downward force of what? 50 kilonewtons. Now, since this force is coming downwards, it becomes minus 50. And this is equal to 34.1 minus 50 will give us minus 15.9 kilonewtons. Now, this same force, minus 15.9 kilonewtons, moves from point C down to point D initially. So you call that shear force D prime, which means initially this same force, minus 15.9, moved down to where? Point D. But finally at point D, this force now encounters what? An upward force, RDY, whose value is also what? 15.9 kilonewtons. So we'll call that shear force D prime prime, which means finally at point D, this same force encounters this same force minus 15.9 encountered an upward force of 15.9. Since it's an upward force, it means you're going to add the value. So it becomes plus 15.9, and minus 15.9 plus 15.9 simply give you what? 0 as the answer. Remember, at the end of every shear force analysis, you must always obtain 0 as the answer. Hence, it means you're wrong. All right, so let's move to bending moment analysis. So we are done with the shear force analysis. Next now is the bending moment analysis. Okay, let's move to the bending moment analysis. From static equilibrium law, the moment of a force about a point automatically becomes 0. But before then, what is bending moment analysis? Bending moment analysis simply means the stepwise summation of the entire moment of forces acting on a beam from beginning of the beam at each point of the beam to the end of the beam. So you always start from beginning to the end. Mind you, whenever a force is acting downwards, that force produces a negative moment. And whenever a force is acting upwards, that force produces a positive moment. And also, at the end of every bending moment analysis, you must always have 0 as the answer. Keep it in mind. So if you don't have 0, it means you're wrong at the end of analysis. All right, let's start. Moment at point A is equal to, now we said moment of a force about a point by equilibrium law is automatically 0. Why is it so? Simply because at a point, any force that exists at a particular position does not have any distance with that position. So the moment of that force at that point becomes 0. So moment at point A automatically becomes 0. And since there is no force behind point A, then the moment of this force about point A becomes 0. But if we move down to point B, same thing happens. Moment of this force about point B becomes 0. But we can now consider the moment of every other force behind point B to take moment about point B. But moment of this force at point B cannot be found. It is simply 0. Similarly, if I move down to point C, moment of this 50 kilonewtons force about point C also becomes 0. But I can consider the moment of these two forces behind point C, which is at B and at point A, to take moment about point C. All right, let's start now. So moment of this force about point A, since there's no force behind, automatically becomes what? 0. So moment at A is 0. Now you move down to point B. Moment at point B is simply equal to, on getting to point B, the moment of this force at point B becomes 0. But I have a force behind point B, which is 25 kilonewtons force, so I can take moment of this force about point B. And since this force is acting downwards, it means it's going to produce a negative moment. So you simply have minus 25. Moment now is force times distance it takes the force to get to the point of moment. Since I'm taking moment at point B, therefore the moment of this force becomes 25 times total distance it takes this force to get to point B, which is 2.5. So I have minus 25 times 2.5, and minus 25 times 2.5 simply gives us minus 62.5 kilonewtons meter. So the moment at point B is minus 62.5 kilonewtons meter. Now I move down to where? Point C, considering moment at point C, and this is equal to the moment of this 50 kilonewtons force at point C automatically becomes 0 because I can't find it. But behind this force, or behind point C, I have two forces, 25 and what? 59.1, which means these two forces can take moment about point C. So we find the moment of these two forces about point C. Okay, since 25 is a downward force, it will produce a negative moment. So minus 25. Total distance it takes this 25 force to get to where? Point C becomes 2.5 plus 3, which is 5.5. So this is minus 25 times 5.5. All right, plus this force now is an upward force, so the moment of this force become positive. Okay, so plus 59.1, 59.1. Total distance it takes this force to get to point C is 3 meters. So multiply this value by 3. So this is equal to, let's now evaluate, minus 25 times 5.5. This gives us minus 137.5 plus, next we find 59.1 times 3. That gives us 177.3, and therefore minus 137.5 plus 177.3. That gives us 39.8 kilonewtons meter. So the moment at point C is actually 39.8 kilonewtons meter. Finally, we find the moment at point D. Okay. All right, so as usual, the moment of this force 15.9 at point D automatically becomes 0. So we simply consider the moment of all the forces behind to take moment at point D, starting from the 25 kilonewtons force. So moment at D is equal to, since this force is a downward force, it will produce a negative moment. Total distance it takes this force to get to point D becomes 2.5 plus 3, 5.5 plus 2.5, that gives us 8. So we have minus 25 times 8 plus. Now at point D we have 59.1 kilonewtons force acting upward, so it's positive. And the moment of this force above point D becomes, total distance it takes for to get to point D becomes 3 plus 2.5, which is 5.5. So we have that to be 59.1 multiplies 5.5. And finally, the moment of the 50 kilonewtons force at point C above point D, this force is acting downwards. So it's going to produce a negative moment. Total distance it takes this force to get to point D is 2.5. So we simply have minus 50 times 2.5. All right, so let's evaluate this and see. Moment at D is equal to, now, minus 25 times 8 gives us minus 200 plus 59.1 times 5.5 gives us approximately 325 minus 50 times 2.5 gives us 125. Now this is equal to minus 200 minus 125 gives us minus 325 plus, put down your 325 here, so plus 325, and of course minus 325 plus 325 simply gives us 0. So once more, at the end of every bending moment analysis, you must always obtain 0 as the answer. All right, so we are done with the sharpness analysis. We are done with the bending moment analysis. Next thing to do now is to what? Plot the diagrams. All right. So I'm going to be putting down all the values of the shear force and bending moment one side. So I can use this portion of the board to plot the diagram. So moment at D, once more, we obtain that to be 0. Let's compile all the results one side here. All right, guys. So these are the values of the bending moment analysis, and these are the values of the shear force analysis. So let's plot the diagrams. So to start plotting the diagrams, first thing to do is trace out all the points with broken lines. So trace out point A, trace out point B, trace out point C, trace out all the points with broken lines. Now let's start with the shear force diagram. Okay, so you start the numbers from the highest to the lowest. Okay, so you look through the shear force values. The only positive result we have here is 34.1 kilonewtons, and that seems to be the highest. And the negative result we have minus 15.9, and we have minus 25 kilonewtons. So minus 25 is the least, minus 15.9 is bigger on the negative side. So first thing first, you draw your origin. So let this be your 0 mark or the origin. Now above the origin are positive values, below the origin are negative values. And the only positive shear force value we have here is 34.1 kilonewtons positive. So you indicate it somewhere here, 34.1 kilonewtons. The next values we have for the shear force are negative values. So starting from the highest, minus 15.9. So you indicate here, minus 15.9 kilonewtons, followed by minus 25 kilonewtons. Okay, so you can indicate that here, minus 25 kilonewtons. So these are all the shear force values. So what you do is you trace them out with broken lines. Trace them all out with broken lines. Trace them all out with broken lines. Now let's start the diagram. Shear force at A is given as minus 25 kilonewtons. This is line A. This is minus 25 kilonewtons. So this is where they meet. You simply asterisk. So you can also do this with a graph sheet to get a proper scaling and dimension, but then freehand sketch is also permitted. Now, shear force at B prime, which means initially at point B, still remains minus 25 kilonewtons. And this is line B, so initially still remains minus 25. You simply what? Asterisk that portion. Shear force at B prime prime, which means finally at point B, the shear force became 34.1 kilonewtons. This is 34.1 kilonewtons. This is line B. See, this is where they meet. You simply what? Asterisk that position. Similarly, shear force at C prime also remains 34.1 kilonewtons. This is line C. This is 34.1 kilonewtons. So this is where they meet. You simply what? Asterisk. Finally, shear force C prime prime give us minus 15.9 kilonewtons. So finally at point C, this is line C. This is minus 15.9 kilonewtons. So this is where they meet. You simply asterisk. Shear force D prime, which means initially at point D, still remains minus 15.9 kilonewtons. This is line D. This is minus 15.9 kilonewtons. So this is where they meet. You simply asterisk. And finally, shear force D prime prime gave us 0. So this is line D. This is the 0 mark. You simply asterisk. Now, take note, the shear force diagram for a point load is simply a straight line connecting all the points. So you simply use a straight line to connect all the points, starting from the origin. So from the origin, we had shear force at A to give us minus 25, which is here. So from the origin, we draw and join minus 25. So you have something like this. Now, this force moves from point A down to point B initially, now encounters an upward force, which gave us shear force at B to be what? 34.1 kilonewtons. You simply use a straight line and you join the 2 points together. Okay? Now, this same force moves from point B down to point C initially. So you move from point B down to point C, connecting all the points. So you have this. Then it encounters a downward force connecting to this point. So you move downwards and you connect to this point. This same force moves from point C down to point D initially. So you move from point C down to point D initially, connecting to this point, and finally to 0 upwards. You have this. So this becomes the shear force diagram. So you can simply shade here. You can simply shade. This becomes your shear force diagram. Let's use SFD to indicate shear force diagram. That becomes the shear force diagram of that beam analysis. Next is to draw the bending moment diagram. So you also look through the bending moment values, picking the highest from the lowest. The highest there is moment at C, 39.8 kilonewtons meter. Lowest is minus 62.5. So we have just two values, one positive and one negative. So as usual, you pick out your origin. So let this be the origin, 0. Above the origin are positive values. The only positive value we have here is 39.8, moment at C. So let's call here 39.8 kilonewtons meter. And below the origin is minus 62.5, negative value. So we can call it here minus 62.5. So trace out all the points with broken lines to the end. Trace out all the points with broken lines to the end. You have this. Moment at A is 0. This is line A. This is 0. So this is where they meet. You asterisk. Moment at B is minus 62.5. This is line B. This is minus 62.5. This is where they meet. You simply what? Asterisk. Moment at C is 39.8. This is line C. This is 39.8. From here, this is where they meet. You simply what? Asterisk. Finally, moment at D is 0. This is line D. This is 0 mark. You simply asterisk. Sorry. All right. The moment diagram for a point load is simply a slant line connecting all the points. So pay attention to the difference. If it is shear force, it's simply a straight line connecting all the points. But the moment diagram for a point load is simply a slant line connecting all the points. So you start from A, okay, you connect to this point, you connect to this point, and you connect to this point. Since they are all point loads, then you have this to be the moment diagram. So you simply what? Shade. All right, so this is our bending moment diagram. So that gives us the bending moment diagram. So we've done the shear force diagram and we've done the bending moment diagram. The final question says, as can be seen on the board, it says also compute the maximum normal stress due to the normal stress tau sigma equals 45 kilonewtons per meter squared. So we have to find the maximum normal stress due to this normal stress. Now we are given dimensions of the beam to be equal to this. Okay, now to find the maximum normal stress, we simply use the equation. Okay, maximum normal stress, sigma max is simply equal to the normal stress itself all over section modulus. Okay, normal stress all over section modulus, where Z itself is called the section modulus. So we need to find the value of the section modulus. How do you find section modulus? Z is simply equal to BH squared all over 6. This is how you find the section modulus, where B is the width and H is the depth of the given structure. So from here, we are given B to be equal to 80 millimeter. We convert this to grand units, meters, simply by dividing 80 by 1000, and that will give us 0.08 in meters. Also, the height or the depth was given as 250 millimeter. Also, you convert this to meters, divide through by 1000, and you have 0.25 in meters. Having found this now, then the section modulus Z is equal to, we said B times H squared, and B is equal to 0.08 multiplied by H, there is 0.25, 0.25 all squared all over 6. So this is equal to 0.08 times, let's obtain 0.25 all squared. That gives us 0.0625 divided by 6. Now 0.0625 multiplies 0.08. That gives us 5 by 10 to the power of minus 3 all over 6. So let's obtain 5 by 10 to the power of minus 3 divided by 6. So this implies that the section modulus Z is equal to 8.33 by 10 to the power of minus 4 in meters cube. All right, so this is now our section modulus. Then we simply plug it into this equation to obtain the value of the maximum stress. Okay, we can do that over here. Okay, so if we plug it into this equation, sigma max is now equal to, remember, the value of sigma was given as 45 kilonewtons, which is normal stress. 45 by 10 to the power of 3 kilo means by 10 to the power of 3 all over section modulus, which gave us 8.33 by 10 to the power of minus 4. All right. If you carry out this division, 45,000 divides 8.33 by 10 to the power of minus 4, you are going to have 5.4 by 10 to the power of 7 newtons per meter squared. So this simply becomes the answer of the maximum stress due to that normal stress. All right, guys, that's it for that particular question 4. I will see you in the next video with question 5. Thanks and cheers.